Oh, sorry. I forget. Things changed in Zoom, so I'm thrown off. Okay, looks like it's recording. All right, so last time we did intro to time series, which I know not everyone was there, but people who did not attend, did you guys were able to watch the recording that I put up on Slack? I see some thumbs up. Okay, cool. So one thing I know I kind of noted is that in the description box, I put like timestamps underneath there, because usually what I'll do is like I'll cut up the video into segments, but I kind of like the timestamp idea. It might take me a little bit longer to put in there, but anyone have any like opinions on like like if they like the timestamps or they prefer when I chopped up the videos, back 2 months ago? He just gave a thumbs up. Does that mean just like cool either way or cool
The
on timestamps?
timestamps were great.
Okay.
Yeah, I love the timestamps. It makes it so easy.
Okay, cool, cool. So I'll keep, I think, I know, I think I talked to Nadine earlier today and she's like, oh, either is fine. Like, but it is nice. But I think it kind of helps a little bit. I might still cut up like this video, for example. I might cut this up in 2 parts just so it's like one section, like section 37 stuff and then section 38 stuff, just so that way it kind of keeps it separated. But I think I'll try to keep the timestamps in there, and that way we'll see in this recording, right? Maybe you'll see the description box and like the little chapters and stuff like that, which I don't know, I think will be good. But cool. All right, let me get the doc going through. Did anyone have any questions from last time, or they put in the doc that I shared last time?
I put one in there, but it's not super important.
Okay. All right, so let's just, oh good. Well, I'll share it and then, because it's going to relate to us doing modeling and stuff. So let me go ahead and share my screen. There we go. Okay. And this is you, Mike, I'm guessing?
Yeah.
Okay, cool. So, all right, so ARMA models, talking about this specific lesson, right? When you're generated. So yeah, we'll definitely talk about this. And then, if we haven't, at the end of the time, if we haven't talked about this specifically, feel free to ask this question as a follow-up and everything. But it looks like, why is the first value calculated? Yeah, so maybe we'll go over this. Maybe we'll answer a few of your questions. So cool. All right, cool. No one else had any questions. That's nice. I think maybe we'll go back a little bit in the future, or in the future, we'll go back to some of the stuff like, I want to talk about pipelines again eventually. I might talk about big data again a little bit, because that's kind of put into PySpark, but I want to talk about how big data beyond just PySpark, I think it's kind of a useful thing to know. If anyone, if you've gone through the Sparks part, I was talking to, I think it was Jeffrey today. If you're going through PySpark, or if you've gone through PySpark and you're like, I don't know what this is, or like, this is a lot of work, don't stress out about it. Like, honestly, don't like freak out being like, oh man, I really need to know PySpark, To be honest, if you're going in an interview and they ask you like, oh, so have you dealt with build big data? A legit answer, and it's perfectly good, being like, not really. You say, I haven't done a really big data project. I'm familiar with some concepts, like MapReduce, parallelism and stuff like this. But if you say like, I really haven't had a chance, most people would be like, yeah, okay. Because it being a first initial data science job, like it's hard to get your hands on big data without basically being already a data scientist. So maybe in 5 years as a data scientist, if you haven't touched big data, then it's a little different, right? They expect it at least some point you touch those tools. But beginning, I wouldn't stress out about it. For your projects, for me personally, I don't ever expect you guys to use Spark. It's actually slower to use Spark on a single computer, the way it works and stuff like that. It only makes sense when you start spinning up a bunch of servers and stuff. So I wanted to add that in there. Okay. Cool. All right, so let me go ahead and start up our Jupyter notebook, because I realize I don't have it on. And I realized, good, okay, sorry, I'm talking to myself. I'm seeing that I don't have the environment set up, or activated. There we go. Okay, so last time we did our intro right here, and you guys all know how to find this, these notebooks, right, on the repo? I know it's been a while since I've done it before. I know, Uma, it's newer to you because I didn't have you before, but just remember you can go to this link right here, and then specifically, last class and this time we'll be talking about time series and statistical modeling. So you can see the different notebooks in here. Okay, so cool. All right, so last time we talked about intro, we talked about like, what time series is, loading the data, talked a whole bunch, right? Versus doing some coding. It's nothing too crazy. It's mostly just making your data focused on the fact that it is about time versus like some other metric, right? That's why we call it time series. So we're going to talk about the second part of section 37, which is trends, because we talked about visualizations, and we're going to talk about what trends are. And I don't think we touched any of that from last time. Let me pin this. And then we'll talk about, once we finish this, we will split off into models, and we'll talk about different models and stuff. And this is probably, well, hopefully we can get through all of it, but at the very least, we'll get through the models basic. Okay, cool. All right, so let me expand this out so it's a little bit easier to read. There we go. Okay, so, oops, let me clear this so we don't have to, we get to run it fresh. Okay, so types of trends. So first thing, I'm just doing some really quick, like just loading up some data. So I'm gonna just import our normal imports, right? Pandas, NumPy, matplotlib. I'm gonna use that New York Stock Exchange from the monthly data. So remember that from last time. And I'm just making sure that we have it to date time. Note, I didn't pass in a format this time because Pandas will figure it out well enough. I think, if I remember this right, it goes month. The other data set, if you remember, there's like day, month, year. Pandas automatically will try to load in like month, day, year, and figure it out. So it's pretty smart. So I don't have to do anything special. We set the index because it's time series for that specific column, which is just the month column. Okay. And then this right here, we're just going to generate some data just to make it nice and fun. You guys remember np.randomSeed, right? It's just so we have the same random numbers, which is kind of an oxymoron, but we'll have the same random stuff, and that way it can be consistent. And then we're going to have some other stuff, so we have some time series data too. Okay, cool. So now we've loaded that stuff, let's talk about actual trends. So let me fold this up. There we go. So types of trends. The first one basically is stationary trends. So there's a good definition of this, and there's actually images on here from this other article. It's very similar to the curriculum ones. But basically, the main idea of a stationary, like the stationary trend basically is kind of that it doesn't change over time. Okay, there's not a pattern directly, the pattern doesn't change over time, if that makes sense. So it doesn't mean that the data is like a straight line. It just means that the pattern is consistent all the way through, time. So there's three criteria that we mostly talk about. The series mean is not a function of time. So if you imagine averaging out these points, right, you would look like something, in a while since I've annotated something, it would look something along the lines of like a straight line, right? Like if you average it out, it basically is like a straight line. You can imagine a straight line just oscillating around the straight line. If the average moves up like this, you can see that like it's oscillating around this other thing. We say this is not stationary, right? So basically it is fluctuating and changing over time. So we say this would not be functionary or stationary. Does that make sense to everyone? Okay, the next one is the variance. So the variance is not a function of time. So remember the variance is basically how much it differs, right? Is standard deviation. So we can see basically, you can almost think of it as like amplitude, and like think of like sine waves and stuff like this. But the main thing is that basically there's not a huge change in how it fluctuates over that mean. So you can imagine the mean here, right? And this one also has a mean that's consistent, but you can see that like basically over this period of time, the fluctuations are much larger versus smaller over here, versus this one over here, it would be a stationary series because it's not changing over time. The variance isn't changing over time. Okay, sound good so far? All right, this last one's probably the hardest one for people to be like, what's going on here? This is the covariance, right? So covariance is not a function of time. And you can think of the covariance as kind of like, the best example of this, I think, is kind of like saying the frequency almost, like how often these things have changed. So you could like, I think looking at all three of these guys, you can quickly say like, oh yeah, it's not consistent over time, right? There seems to be some change where at the beginning of time, like it seems to be slowly changing. And then like, as we get closer in time, it's changing a lot frequently, right? That's what this covariance is. And covariance basically is like the variance of the variance, if that makes sense. So like things are changing at a different rate and stuff like this. Don't worry too much about specifically trying to like pull these out from here. The nice thing is that we're going to use tools that will later decompose into these three separate parts. But the important thing to note is the reason why we care about this, why we want a stationary series, is because we want to basically remove anything that can be predicted already with time. Like if you think about this, we might actually have a prediction over time. If this is random, so you can see this is like really nice and predictable, but if this is random, let's say for example, the variance does change and it seems to randomly distributed, we say that's still stationary because there's not a pattern over time in the variance. Does that make sense to people? Okay, so our goal is to do stationary so we can actually apply certain tests and do certain interesting things. Okay, all right, cool. Are there any questions on the stationary concept? No? Cool. All right, I'll move on then. So one is a no trend, right? And so no trend is basically kind of like what we're saying is like there isn't a trend over time. And so it looks more or less random essentially. And that you basically can't predict the pattern from just looking at what time it is or where it is in time. So it seems kind of weird, but that's what we actually want. We want something where we can break apart the no trend. And the reason why I kind of phrase it this way is because if you think about it, if you can predict it with time, right? If you can take out the say like, oh, we can take out the fact that we know it's increasing over time. We know it's going to be changing in variance over time, like in a certain predictable way. Then you know something about the series already. And then we're left with all this extra fuzz and stuff. And you say, oh, these are things we don't know. And that could just be, if you were talking about physics, you say, oh, like the accuracy of our instruments or something like that. It could be other factors and other data science, like other features that we're not accounting for, or it could just be random noise in the sense that like random noise is like, there are things that we're not accounting for, okay? And that's where the interesting stuff comes through. All right, so besides like no trend, which is kind of like not really that exciting when you think about it, you want to see like, oh, you want to see a picture visualization, and visualizations are really good at like seeing these things. It's a linear trend. And as you probably can guess, a linear trend is you're going up like a line, right? So basically it's very similar in the sense that like there is a trend and they say, oh, there is a trend upwards for, in this case, these are pictures from the curriculum, by the way. This is UK imports and then over the year. So you can see there's more UK imports over years. So knowing nothing else, and there's still fluctuation, but you can say in general it's going to go up and you can average this out, for example. Similar downward trend, you don't have to really make that too complicated. Okay. Next one is exponential trends, which are really interesting because they also are increasing over time in this case. But what's really interesting about an exponential trend is that if you're part of an exponential trend and you have it over a smaller period of time, so for example, we look at just 2012 to 2014, if you were to zoom in on that, this looks like just a linear trend, right? It doesn't look particularly exponential. And that's a really big factor of exponential. And it comes from the fact that in exponential, if you guys remember, a lot of time in math, we'll just use the e, right? So natural number to the power of some variable like x. E to the x, when x is very, very small, it equals about x. Like it's about the same for very small numbers. And then as we get bigger and bigger x, that's when these two diverge from each other. So what tends to happen, and it's fun to talk about this because with coronavirus, COVID-19 going on, we can kind of see a little bit of this prediction, is that early on in the days of a time series and an exponential trend, you look at it and like, oh, it looks linear. Like it looks like we can predict it over. But what tends to happen if you think it's linear, but it's actually exponential, if you were to extend this like model out, right, to a linear form, you'll see that you eventually become more and more like completely off, right? And you can see instead that the real trend was closer to kind of going up on this curve like this. And this is where people talked about with models for like COVID, is that they were worried about like, hey, this should be an exponential trend. But unfortunately, sometimes people who might not know the necessarily mathematics or are familiar with this kind of like the epidemiology and stuff like this might look at this like, well, it's not really increasing that much. It's not really changing that much. And it's not until basically, essentially further in time where it's too late in the sense where it really takes off and it happens very suddenly, very quickly. Okay. Makes sense. So as a data scientist, your biggest thing is always thinking about like when you think exponential, when you see a trend that's like linear, you should always think to yourself, should it be linear or should it be something else? Because this is a really easy mistake to make. Like, oh, you think of like if you had this model, and let's say this is like your days, it's like, the 8th day, and you think, oh, it's a linear trend, but in fact it's exponential. By the 8th day, you are completely off. You might as well have just completely like not done anything. So that's an easy trap for data scientists to fall into if you're not careful about what the context of your data are. Okay. Periodic trends, as you probably guessed, are this periods, right? So you can see it fluctuates throughout the time. So this is the temperature over, different years, right? And you can see temperature goes up, then goes down, and so on and stuff. Yeah, and you can still see there's fluctuation stuff. This one's also interesting too, because you can see that there's kind of two trends going on here. This one's a little more stationary in the sense that like there is a period, right? And there's some fluctuations, but it's basically averaged about the same. It doesn't seem to be going significantly up or down or whatnot. And this one right here, you can actually see that there is a trend upward as well as a period going up and down, Okay, cool. All right, so those are different types of trends that we're gonna really focus on. Any questions at all that came across these first few parts? Feeling pretty good? Yeah. All right, cool. So let's talk about assessing trends. So we have this data set, right? So this, in this case, is the New York Stock Exchange monthly data, right? And I just plot this out and you look at this and you're like, is this a stationary trend or stationary series? Maybe. Like, obviously we're gonna be a little more quantitative on this, right? But it's not necessarily easy to say, well, okay, maybe there's a pattern in there that we can pull out, but maybe not. So this is where we can do certain things like observe those different trends and see like, well, is there a trend in here? So one really, really common, really powerful way is rolling statistics, okay? And so the idea here is that we take a statistic of, I think of it like a rolling window. So imagine we have a little like window, like we look at just this part of the data set. And then we kind of move this window over and we kind of move it over and say, okay, let's look at this part of the data set, right? And we basically use that. So that's rolling statistics. You essentially are rolling this window over the data set and looking at the statistics for that as a group. Okay, remember statistics is going to be a group of things, right? You're never looking at one thing in the statistics of that one thing. It's always going to be like a group of stuff. So commonly I say average on here, but it really doesn't have to be average. It could also be the standard deviation or other metrics. But usually it's like the average number of like, like the average in these number of data points over this time period. So it's easier to see an example and you can see rolling window, right? So in this case, I'm going to do the rolling mean, and then this is our time series TS dot rolling window equals 6. So what that's doing is it's taking the next 6 data points and it's going to take the average, the mean of those points together. And it's going to do that for the first 6, and then the second one to the 7th one, the third one to the 8th one, the 4th one to the 9th one, and so on, right? So this window is going to keep moving. So we'll actually get 6 points less than what we had before, right? Because it's going to basically have those first 6 points are going to be combined into one. I should say 5 less points. It'll move over. And if we let it keep going past, let's say you're at like the last point, you can potentially say, oh, let me take the average of the last one plus 5 other points, which don't exist. And you can say, oh, the average of that one point is just that point. So that's what that looks like. And then we can do the same thing with standard deviation. Okay. So we can take standard deviation of those. Well, I'll put 6 here. I don't like putting 1. I think it's probably playing around there. All right. And then what I'm going to do here is I'm just going to plot out each one. So I'm going to plot out the original data set, right? So we're going to plot that in blue. We're going to plot the rolling mean, right? So we're going to see the mean, how it changes. Then we're going to see the standard deviation in black. Okay. And so we do this guy, and you can see now we have our blue data set. This is the original, and you can see it's very, very, chaotic, not chaotic, but like it's fluctuating, right? And you can see the red one here. It kind of rolls over, right? You see it's a little smoother, and we can see the overall trend here. So this is really useful when like you have a little bit of noise, like for example, if you have like the temperature every day, like that might be a little too much information versus when you're looking for the whole year. You might do a roll statistics from every week, like oh, every 7 days we're going to roll this over, take the average over this way. There's a whole bunch of reasons why you might do this, but it's a very quick and very common technique for time series. Note that also the black right here, I'm taking the standard deviation, right? So I'm taking the standard deviation of those 6 points to see how they differ from each other. And you can see here, there doesn't seem to be too much variance, at least in this on the scale of how the variance changes, right? So you can see the standard deviation is pretty consistent with this rolling statistics. It's kind of important to, if I put this to 1, you can see that our standard deviation doesn't even show up because like it's just a rolling window of 1. But if I do 2, you can probably see a little bit of something here. And you can see 2 data points are going to have a lot more variance because there's only 2 data points, right? They can fluctuate from each other. You can look at these 2 data points and see that there is a difference between those 2. Okay. Any questions on this rolling statistics? So one thing I'll kind of get a little test, right? So I have this window right here of 6. You can ignore the standard deviation right now, but I have this little window of 6, right? If I were to make it, let's see here, smaller, let's say 3, what do I expect the red line to be? What will change about the red line from what it is right now?
More noise.
Yeah, more noise, like more fluctuation, right? And that's because we're looking over a smaller number of points, right? What happens if I change this window to 1? What would that end up looking like for the red?
The same as the blue.
The same as blue. And I saw Andy and Mike both unmute themselves too. So I think probably
Sorry,
you guys are
guys.
thinking the same thing. No, it's not good, guys. So you can see here, that's exactly right, because it's literally just 1 point. So of course it's going to be the same one. Let me ask you guys, if I put like 10 here, like, so I'll go back to 6 real quick. And I put something, let's just say, let's just put like 16. Okay. What's going to happen to this red line? And how about someone who hasn't said anything yet? That way.
It'll be smoother.
It'll be smoother, right? It's definitely be smoother, right? So I want you to pay attention to where this looks like. So right now, the red line looks really close along this blue, right? Okay. Watch what happens when I run this as 16. So first of all, Andy's right. It gets a lot smoother, right? But note right here, this ended up being a lot, like it almost like fell down more if you guys look at that, right? It doesn't seem no longer with this. Anyone explain like what's going on here? Like why is it no longer with this blue trend line or blue data series?
It's not keeping up with the change.
Yeah, so this is an interesting one because we're taking an average, right? The dot mean. The dot mean basically is weighting every point exactly the same. So the thing is that these, in a sense, these data points from the 6 prior windows, right, or 16 or whatever, how far back, are significantly smaller. They're basically outliers compared to like, the current, the most recent stuff. So those are going to bring down the overall data right here downward. And so especially in an exponential trend, this will get flatter and flatter and actually bring down, you'll underpredict. So we'll actually talk about this, I think, in a second. But one solution you can do is not taking our arithmetic mean, which basically means everything's weighted equally. You give more points weighted towards more recent points. So like those points will get more of a bump going up, and that will help bring it back up closer to what's recent. Because imagine if you took this trend right here, this model, and you try to extend it outward, you're going to underperform, right, what this model originally was. Well, not this model, this data actually should be doing. Okay. So I thought it was an interesting point to point out. Okay. And just to show you guys 6, it does the same thing too, but less so because you're looking for 6 current points. Okay, cool. All right, so let's move on to Dickey-Fuller tests. So Dickey-Fuller tests, I think it's always one of those weird ones because it's like a double negative. It's a statistical test. So remember, for statistical tests, we're still looking for the p-value and saying basically from the null hypothesis, whether we reject it or fail to reject. Remember, we never accept the null hypothesis, right? We just reject or fail to reject because of science. Like that's equivalent like what we're doing. It doesn't necessarily mean the null hypothesis is not true with 100% doubt. It just means like, oh, this doesn't seem to explain the null hypothesis, or the null hypothesis can't explain this data easily. It's possible, but unlikely, okay? So the null hypothesis is that the time series is not stationary. So I want you kind of like think about this for a second. Like your null hypothesis H0, right? H naught is testing for this time series. And if we reject, if we have significant value, right? So a low p-value, right? Then we would say, oh, it is not it's not stationary. We reject this not stationary condition or hypothesis. Does that make sense? So what we usually want is we want it to be stationary. So if we have a low p-value for the Dickey-Fuller test, then it means that we have a stationary, at least we are reasonably certain that we have a stationary time series. Does that make sense? Okay, cool. There's other tests you can do. This is just one of the tests. It's a very common one. So just know that this is not like, oh, this is the end all be all of like hypothesis tests for testing stationarity. You can spend a whole lifetime on talking about time series and all these different things, and people do, because one big reason is because finance, and with finance means money, and if you can make more predictions on money, people really care about that. So part of the reason why people have a lot of effort on that. But just to call this over, this is from the curriculum, so I'm not going to spend too much time. But we have the add-fuller basically from stats and models. So stats models, remember, is like a statistical package. So it has a lot of great things that basically SciPy and scikit-learn don't have and everything like that. But basically what I'm going to do here is we have our series from, we have our test right here. So we're doing the actual test. This is the Dickey-Fuller test. Okay, I know it doesn't seem like AD Fuller, but that's what it is. And then we just get the results right here from the time series. And what we're going to do with this guy is basically just extract it so it's easier to read. So I'll kind of show you guys what it looks like first. And you can see here that basically gives a bunch of results right here, right? And so this is what DF tests would give, but this isn't very readable, right? And this is where stats models is great, but like it's not super like, how do I explain this? Stats models seems more like a statistician's programming stuff versus a programmer making statistics stuff. So that's why like you see this part like I don't know what this is, right? Like there's numbers here, like this clearly it's like a confidence interval or something like that, right? But it's kind of hard to tell. So this is where you can see from the curriculum, if you actually look at the, what's it called? The doc, right? You might see a little more information about like what these results are. So there's the parameters and returns, the ADF, the p-value, the critical values, and all that stuff. So we just shortcut that from the curriculum here. We say that's the test statistic, is this guy. Well, I'll show you, this is easier to read, right? So now we have a nice pretty data frame, right? Where we can read it, or technically it's a series, but it's a little bit easier for us to read. So you can see this test statistic, which, let me ask you guys, does the test statistic really matter for us when we look at it? Probably not. It's hard to interpret unless you actually are familiar with the test. So the one that I really care about is the p-value, right? So the p-value is saying like, okay, like do we reject or fail to reject this null hypothesis, right? There's also some extra stuff like number of lags used and stuff like this. And this is more specific to the Dickey-Fuller. I'm not going to go into detail because I don't think it's super important for what we need to do. But you can see some extra information about here too. But the main thing we care about is the p-value. And so the p-value is 1.0. So how do we interpret this? Any kind of idea?
Don't reject.
Right.
Don't reject.
It's a, we
Go
can't
ahead.
reject.
I'm sorry, Nadine. Go ahead and say that one more time.
I was saying usually we set alpha as like 0.05 for something really small. This is 1, so it's big. So we can't reject the null hypothesis. So we have to keep H0 that the time series is not stationary.
Good. Perfect. And that's actually a really great way to phrase it too. Like if you are part of like, if you're writing statistical like output, you would probably write it like we fail to reject our null hypothesis that the time series is not stationary, and therefore conclude that it is likely, you know, like not stationary because their p-value and whatnot. But yeah, p-value of 1.0 is basically as high as you can really get at, right? Like it's a pretty big p-value. But if you had something more significant, so that means is that our TS, which I believe is this guy right here, this shows that it's not stationary, which, I mean, you look at this, right? Like it's gotta be, like, if someone told you this was stationary, you'd probably look at it like, that's really weird, right? Doesn't seem likely that would be stationary, right? Am I wrong interpreting that? Like you guys look at this, like that's definitely not stationary. Like, I mean, look at this, right? It's like, it's literally this thing right here, like, which is like not stationary. So that makes sense. So let's try it with the New York Stock Exchange data, which I believe I can just take data here. I've already loaded it. And let's do data. Make sure I don't have anything weird. Oop. Oh, that's why I didn't do it last time. All right, never mind. If you could do this, well, do you guys want me to move on, or do you guys want to see what it looks like for data?
Let's see it. Will it
Okay.
take a long time? Or? Yeah,
Yeah, let's see.
it.
All right, we got data. We just want month. Oh, gosh. Dot iLock. So I'm taking the very first. Oh no, I don't want. Sorry, I want the second one. So what was it? Monthly return. So I'm just taking. The problem is that it's looking for just a series, right? So let's call this new data. or new TS. There we go. Okay, so the reason why it was, if you guys saw this before, so I'll just quickly show you what that error was and why it's like, oh, that's right. This, it says, you guys know how to read errors now, hopefully at this point, is that whenever you see an error, skip all this stuff first, goes right to the bottom, where it tells you like the summary of what the error is. Value error, too many values to unpack, expected 2. Oh, okay. What's happening is that there's too many columns essentially. So, and then if I go into there, you could look a little bit deeper, but it doesn't really matter, right? So you can see this is what we want. So I just got just that part. So we get, oops, new TS. Okay, and there we go. We see right here our points, and let's just go ahead and do the output. And you can see here, okay, test statistic. Okay, again, I would never really pay too much attention to this unless you know about Dickey-Fuller and like the distribution of it. The important part for us, because it's already calculated for us, is the p-value. And you can see, is this p-value small or big?
Small.
Small, right? Which means interpretation time.
It means that we can reject the null.
Yeah, we reject the null, which interprets into
That it's not stationary.
that. So we conclude it's not stationary.
Yes.
It's the opposite. So we conclude that we reject the null. I know it's confusing, right? We reject the null hypothesis that it's not stationary, which means it's not stationary, or more accurately, it's unlikely to a certain degree that it's not stationary. Okay, so, and you can see that p-value is pretty small. So even like Nadine mentions like an alpha of 0.05, we would definitely reject this because the p-value is smaller than 0.05. In fact, there's very few p-values you would probably have where you wouldn't reject this. And that makes sense. If you look at this, this was pretty much my example of being like, yeah, it kind of looks not stationary, right? No trend. So, or sorry, it looks stationary. It looks like no trend. Okay. Cool. Any questions on this? I kind of wanted to make sure we go over it, but I wouldn't stress too much about it by itself. This is useful when you want to feed this into a model that requires your time series to be non-stationary. So we'll actually talk about decomposition. We'll actually take out like the stuff that makes it not stationary. Okay, which is called removing trends. Okay, so removing trends, and we'll go through this. Yeah, we're a little, got 20 more minutes. Well, we can go through here. So removing trends. Our goal basically is to take a time series and to make the time series stationary to the most, for most models, they need to have a stationary time series. Otherwise, it's like you're just using the time patterns, right? So there's two things called the seasonality and trends. So trends are kind of like the overall reach. The seasonality is kind of like the period, like kind of like short term, right? Think of like your seasons, right? Seasonality, and then trends for like year to year to year. Okay. So quick check, why do we want to get stationary series? Like I said, we just want to leave just the noise. We want just the interesting stuff that's not time related. And then we can model essentially that noise, right? I call it noise, but it's not really noise, but that noise that's not related to the time itself. And then I mentioned think of stationary like independence, right? So an independent from, like it's not dependent on time anymore. So stationary means like it's not moving, right? So it's not dependent on time. That's what I mean by independence. All right. So one thing we can do is log transform. So log transform basically, as we talked about before, penalizes really high values, right? And it's very similar to like a square and cube roots. In fact, I think I show an example of using a square root transformation, which is kind of similar, just doesn't punish it as much. Log transformation basically is like the most like punishes the highest values. I don't know if that makes sense, but we're just going to plot this out. You can see np.log, just apply it to the time series, nothing too special. And we have right here, I believe this is the original data set. Yeah, here's the original, so we can see exponential. And you can see that afterwards we have a lot smoother, right? It's no longer exponential going up like this. And we can see it's a lot more like a straight line. And then square root right here, you can see similar, though there's a little bit of extra. If this was really exponential, you would still probably see it going up. But the log transformation usually tends to do really well. Now note one thing is that you also are going to punish these higher, I could get a lot of like fluctuation. You might still punish some of those, so you can see like the variance here is going down. But now we get into a nice form where, okay, like if we take the log of this data set, we get something that's closer to like, you know, we can modify and get an idea of like where this is. But it's not quite stationary, right? It's still got this linear going on here, but at least a little simpler. Okay. Another strategy is to subtract the rolling mean. So we talked about doing the rolling mean, right? So we'll have this guy right here, and we talked about this rolling mean, in this case, a window of 4, right? And what we can do is we can basically subtract off the rolling mean from the original data set. And what that means is that, like, we have this data point right here, and we're just gonna see the difference from the rolling mean. So because the rolling mean is gonna keep kind of like the previous data points and kind of follow it upwards, you can see this kind of exponential part. It basically means that we're just gonna see how far does it fluctuate from basically looking at the previous points. Does that make sense? So, because that's really what the rolling mean is doing, just looking at the previous points and averaging them out, right? So when we do this, we can see then, I'm getting rid of the null values, because what happens when I try to subtract the rolling mean from here? There's nothing there, right? So I'm getting rid of those null values that don't actually exist. And then I'll plot this out. So this should only see the difference from that mean. And you can see here, like you can see the scale in here, like from like 2 to 3. And you can see here, these are all like under 1.0. And this is basically showing the fluctuation from that rolling mean. Does that make sense? Okay. So again, this is a little bit easier. It's like, oh, well, we can predict basically, like you can think of it this way, is that like, imagine these are stock prices. If you know the prior 4 days, you know, maybe a week before, you can use those prior days, say, well, it's going to be, this is the average over those past 5 days. What's it going to look like for the future? Like how far off will we be? And this essentially was what kind of like what we'll see. Okay. Or at least what we predict we'll see. All right. I mentioned before, weighted rolling mean can be really useful, especially when the current or like the most recent changes are like most recent data points are the most important. Think of like stocks. Do you care about the stock from like 2 weeks ago to predict the stock of today? Yeah, a little bit, but you probably care more about the stock from the previous day to know what today is going to be, right? Like it makes sense. Like the more recent stuff is probably the more important stuff. That's where a weighted moving average, right? So a weighted mean. So you can see exponentially weighted mean moving average, EWM. Basically, it just allows you to have, it bumps up the more recent points and kind of doesn't care too much about the old points. Okay, I just wanted to add that in there. All right, so all sound pretty good so far? Cool. All right, stop me if you guys have any questions at all, right? So don't feel bad to interrupt me. All right, so differencing, so kind of similar to kind of subtracting off the rolling mean, except we're just looking at like the one prior, right? So you're just looking at like the previous one. It's also called lagging, okay? We're just looking at seeing the difference from the previous day. So just to show you an example, just to quickly look at this, we have this New York Stock Exchange, right? This is basically just how much it differs from the previous day, which it turns out this kind of modeling, if you look like one of the metrics, like you think your baseline model, it's just looking at like what was the prior day and just predicting, let's say the stock traded at like $100 per share, right? And you say, well, okay, yesterday it traded for $100 per share. Maybe today it will trade for $100 per share. That's actually a really good model. It turns out that's actually a really hard model to beat. You can do a whole bunch of really crazy stuff and still not be able to beat, basically just use yesterday's value, and that's fine. So note that basically this is actually a really valid prediction sometimes. Just like look at the prior day and see what it does. So interesting stuff. In this case, temperature over a decade, I just have a different data set, I think. So min temperature, and there you go. You can see here, this is our temperature, this is the original data set, and you can see our fluctuation from just looking at the prior day, which in this case is still pretty, it looks like we actually still have quite a lot of fluctuation. I actually don't know why it's so much fluctuated, but did I do this right? Sorry, I'm just making sure I didn't have like something crazy in here. Let me just make sure. Oh yeah, that's a lot worse. Okay. Because you can see there's a lot, it should be day first, so yeah. So there we go. But you can see at least there's a lot less fluctuation, right? Or like there's less periodicity, right? Less seasonality amongst the time and stuff like that. There's still some fluctuation and stuff like this, but this is just literally looking at, let's look at the yesterday and predict min temperature from yesterday. And so sometimes it does really well. You can see kind of like it being a little darker right here, but sometimes it doesn't do very well, right? You can see like maybe the next day it got really hot or the next day it got really cold. Okay. Cool. All right. So that is differencing, and then time series decomposition. So I talked about like how you can do these things, like basically take apart like, you know, a thing and make it seasonality. A really cool tool is basically just make it do it automatically. And basically you can do decomposition and say, hey, I want to take out the seasonality of it. I want to take out the trend, and I want to basically just leave out the noise, right? So basically the 3 parts of a time series really is like how much, what's the seasonality of it, what's the trend, and then all the extra stuff, which I call noise, randomness, irregular, the remainder, right? The main thing though to know is that, is the model additive or multiplicative? So if it's additive, it means that it just increases from the previous one. Multiplicative is basically you get a bigger and bigger change as we go forward. So for example, you can see here in this diagram from the curriculum, you have wider, bigger and bigger like fluctuations, okay? This might happen, for example, like let's say this changes with population, right? Or like, let's say like there's an off season or an on season. So there's like a really big on season and then like not that many people, and then a really big on season and then not that many people. And so if the population grows over time, like significantly, you will still see that on and off, but those swings might be a lot bigger, where maybe there's like 90% of the population doesn't do this thing. Like, well, that 90% is going to be a bigger number of people, if that makes sense. So it's multiplicative versus like additive. So a good example of this is passengers, right? So this is like plane passengers, right? Or passengers on a plane. And you can see from 1949 to 1961. And you can see here that there's definitely a fluctuation, which we kind of think of like season, like with planes and stuff like this. You can probably guess that there must be some seasonality to it. Think of like all the people going for like different holidays and stuff like this, or travel times or whatnot, right? There's definitely some seasonality into this. But as we get bigger and bigger, we can see here is that we have bigger and bigger swings because just more people in general are flying planes. Does that make sense? Or flying in planes. Okay. So does that make sense to people? Okay. And this would be obviously a multiplicative trend, right? It wouldn't be additive. Well, yeah, because it's getting bigger and bigger. So just to kind of look at, like, we could do this manually. We can do a log transform. Say, okay, look, it's a little bit better, but you can see here, and still we got that fluctuation. You see the linear trends. Okay, let's go ahead and try to do the seasonal decomposition. So in this case, I just made it so it's a little bit easier for us to deal with. Exponential trends are a little harder to like do automatically. So we make this as a seasonal trend. I'm sorry, it's a linear trend with seasonality. And so what this is right here, the stats models can actually take out the seasonal decompose. And we can say, okay, let's take np.log of ts, which is this guy, and we get the trend, the seasonality, and the residual. The residual just being like random noise. And we can actually plot this out, and you can see, hey, check that out, all automatic. So here's the original, right? Original after log transformation. We see the trend, we see the upward trend, we see the seasonality, and then this is the noise. Pretty cool, huh? Like, I didn't have to do anything. I could wipe my hands with it. Cool. An interesting one you might look at right here is this right here, like, cool, like population's going up, more people. Oh, we have seasons right here. This is usually where the money is. You're like, what's going on right here? And this is the stuff you think about. All we had were basically just number of passengers in the time. And you look at this and you're like, but what's this fluctuation from? Like what's happening here? And this is where we can go around. If we had more time, we can talk about like what possible things we should look at. What other features should we look at for these time periods? I'll tell you what, I don't know, at least one other person talked about. It's like the 1950s, like it's so low. Like, was there like a travel embargo, or like was something about like, you know, maybe certain places were not accessible during this time? Maybe something to deal with Cold War, like, you know, like what's going on right here? Maybe there's something to deal with this, you know, past few years, right, in this middle, in the US at least, assuming this is from the US. So otherwise you can kind of see it's not too much, but this part right here, 1954 to 1958, seems oddly suspicious of like, it's so much smaller over these small periods. So maybe there's something going on here. And this is where domain expertise would be really useful to say, oh, well, that's the next thing to investigate. Okay, cool. Make sense to everyone? Yeah, cool. Yeah, how nice is this like automatic like decomposition, right? Like, yeah, don't do this yourself. Like, have tools do it for you. Okay, let's see here. Yeah, so one thing I said, like the residuals look stationary. Technically, you should probably do something tests to formally say it is stationary. So I'll just run this code right here. It's from what we had before. We look at the number of passengers after the decomposition, right? We're looking at just number of passengers. Yeah, just to make sure. And so we run this guy. We should see our p-value is pretty small, which makes sense. This looks non-stationary. Or sorry, this looks stationary. So, cool. All right, sound good? Any questions? All right, cool.